NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial. Today we're going to explore a special case of polynomial divisibility. Specifically, we'll examine when a cubic polynomial can be divided by the factor x plus 1. Let's start with our theorem. If we have a cubic equation of the form ax cubed plus bx squared plus cx plus d equals 0, with the condition that a plus c equals b plus d, then the equation is divisible by x plus 1. Now, let's prove this theorem. If we divide the cubic equation by x plus 1, we should get a quadratic equation with calculable roots. First, let's rearrange our condition. From a plus c equals b plus d, we can solve for d, getting d equals a plus c minus b. Now, let's substitute this value of d into our original cubic equation. Next, let's rearrange the equation to group similar terms. We can rewrite it as ax cubed plus a plus bx squared minus b plus cx plus c equals 0. This can be factored as a times the quantity x cubed plus 1, plus b times the quantity x squared minus 1, plus c times the quantity x plus 1 equals 0. Now, let's factor the first two terms. We can express x cubed plus 1 as the product of x plus 1 and x squared minus x plus 1. Similarly, x squared minus 1 can be written as the product of x plus 1 and x minus 1. Notice that x plus 1 is a common factor in all three terms. Let's factor it out to get x plus 1 times the quantity a times x squared minus x plus 1, plus b times x minus 1, plus c equals 0. This shows that x plus 1 is indeed a factor of our original cubic equation, which means the equation is divisible by x plus 1. The quotient when we divide the original cubic by x plus 1 is the quadratic expression ax squared. This shows that x plus 1 is indeed a factor of our original cubic equation, which means the equation is divisible by x plus 1. The quotient when we divide the original cubic by x plus 1 is the quadratic expression ax squared plus the quantity b minus ax plus the quantity a minus b plus c. Let's verify that our result is correct by expanding the factorized form back to the original cubic equation. When we multiply x plus 1 by our quotient, we get ax cubed plus bx squared plus cx plus a plus c minus b. Comparing with our original equation, we have ax cubed plus bx squared plus cx plus d. Since we've shown that d equals a plus c minus b, the factorization is valid. There's an alternative approach to finding the quadratic equation without performing the full division. Using the formula, we can directly write the quadratic as ax squared plus the quantity b minus ax plus a minus b plus c equals 0. Let's work in the formula. We can directly write the quadratic as ax squared plus the quantity b minus ax plus a minus b plus c equals 0. Let's work through an example to better understand this concept. Suppose we have the cubic equation x cubed plus 2x squared plus 3x plus 4 equals 0. First, let's check if the condition a plus c equals b plus d is satisfied. In this example, a equals 1, b equals 2, c equals 3, and d equals 4. So, a plus c equals 1 plus 3, which is 4, and b plus d equals 2 plus 4, which is 6. Since 4 is not equal to 6, the condition is not satisfied, and the polynomial is not divisible by x plus 1. Let's try another example. Consider the cubic equation x cubed minus 3x squared plus x minus 3 equals not satisfied, and the polynomial is not divisible by x plus 1. Let's try another example. Consider the cubic equation x cubed minus 3x squared plus x minus 3 equals 0. Let's check our condition. Here, a equals 1, b equals negative 3, c equals 1, and d equals negative 3. So, a plus c equals 1 plus 1, which is 2, and b plus d equals negative 3 plus negative 3, which is negative 6. Since 2 is not equal to negative 6, this polynomial is also not divisible by x plus 1. Let's try one more example where the condition is satisfied. Consider the cubic equation x cubed minus x squared minus x plus 1 equals. We'll solve this step by step following a specific factoring method. Let's begin by examining our cubic equation. Here's our problem x cubed minus 6x squared plus 5x plus 12 equals 0. We'll use a special factoring method to solve this cubic equation. This method involves finding a way to rewrite our cubic equation in the form of a product of a linear factor and a quadratic factor. Let's recall the general form of a cubic equation. We have ax cubed plus bx squared plus cx plus d equals 0. There's a useful rule for cubic equations. If a plus c equals b plus d, then we can factor the equation as a product of x plus 1 and a quadratic expression. In our example, let's check if the condition a plus c equals b plus d is met. We have it equals 1, b equals -6, c equals 5, and d equals 12. So a plus c equals 1 plus 5, which is 6, and b plus d equals -6 plus 12, which is also 6. Since both sides equal 6, the condition is satisfied, and we can proceed with factoring. Now, according to the rule shown in the image, we can rewrite our cubic equation in the form x plus 1 times the expression ax squared plus quantity b minus a times x plus quantity a minus b plus c equals 0. This factorization form comes from the property that if a plus c equals b plus d, then the cubic can be factored using this specific pattern. Let's substitute our coefficients into the factored form. We have it equals 1, b equals -6, and c equals 5. So b minus a equals -6 minus 1, which is -7. And a minus b plus c equals 1 minus -6 plus 5, which equals 12. So our factorization becomes x plus 1 times the expression x squared minus 7x plus 12 equals 0. Let's verify our factorization by multiplying it out. When we multiply x plus 1 and x squared minus 7x plus 12, we should get our original equation x cubed minus 6x squared plus 5x plus 12 equals 0. First, we multiply x by each term in the second factor. X times x squared gives x cubed, x times -7x gives -7x squared, x times 12 gives 12x. Then we multiply 1 by each term in the second factor. 1 times x squared gives x squared, 1 times -7x gives -7x, 1 times 12 gives 12. Adding these up, we get x cubed minus 7x squared plus 12x plus x squared minus 7x plus 12, which simplifies to x cubed minus 6x squared plus 5x plus 12 equals 0. This matches our original equation, confirming our factorization is correct. Now that we've factored our equation, we can solve it. Since the product equals 0, either x plus 1 equals 0 or x squared minus 7x plus 12 equals 0. From the first factor, we get x equals -1. For the second factor, we need to solve x squared minus 7x plus 12 equals 0. We can factor this quadratic as the product of x minus 3 and x minus 4 equals 0. So from x minus 3 equals 0, we get x equals 3. And from x minus 4 equals 0, we get x equals 4. So the solutions to our cubic equation x cubed minus 6x squared plus 5x plus 12 equals 0 are x equals -1, x equals 3, and x equals 4. Let's summarize what we learned. We solved a cubic equation using the factoring method. We identified that when a plus c equals b plus d, we can factor the cubic equation as a product of x plus 1 and a quadratic expression. We verified our factorization by multiplying it out. Then we solved the resulting factors to find the three solutions x equals -1, x equals 3, and x equals 4. This method is very useful for solving certain types of cubic equations without having to use the cubic formula. Today, we're going to solve a cubic equation using a special factoring technique. Let's get started with our example. Let's begin by looking at the general formula for factoring certain cubic equations without having to use polynomial division. We can use this formula for a cubic equation of the form ax cubed plus bx squared plus cx plus d equals 0. If the condition a plus c equals b plus d is satisfied, then we can factor it using a special pattern. When this condition is met, the cubic equation can be factored as follows. X plus 1 times the quantity ax squared plus the quantity b minus a times x plus a minus b plus c equals 0. Let's see how to apply this to our example. Now, let's look at our cubic equation x cubed minus 3x squared plus 2x plus 6 equals 0. We'll first identify the coefficients. In our equation, a equals 1, b equals -3, c equals 2, and d equals 6. Let's check if the special condition a plus c equals b plus d is satisfied. We have a plus c equals 1 plus 2, which equals 3, and b plus d equals negative 3 plus 6, which equals 3. So, a plus c equals b plus d, and the condition is satisfied. This means we can use our special factorization formula. Now, let's apply the factorization formula to our equation. According to our formula, the equation can be written as x plus 1 times the quantity 1 times x squared plus the quantity negative 3 minus 1 times x plus 1 minus negative 3 plus 2 equals 0. Simplifying this, we get x plus 1 times the quantity x squared minus 4, x plus 6 equals 0. Now we can find the roots of this cubic equation. From the factored form, we can see that x plus 1 equals 0 is one solution, which means x equals negative 1 is our first root. For the second factor, we need to solve the quadratic equation x squared minus 4x plus 6 equals 0. We can use the quadratic formula x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's apply the quadratic formula to our quadratic equation. 4x squared minus 4x plus 6 equals 0. We have a equals 1, b equals negative 4, and c equals 6. Substituting into the formula, we get x equals negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 6, all over 2 times 1. Let's simplify the expression inside the square root. We have negative 4 squared, which is 16, minus 4 times 1 times 6, which is 24. So, 16 minus 24 equals negative 8. Since the discriminant is negative, the quadratic equation has no real roots, which means the cubic equation has only one real root x equals negative 1. So, our final answer is that the cubic equation x cubed minus 3x squared plus 2x plus 6 equals 0 has only one real root, x equals negative 1. The other two roots are complex numbers, which we can find by completing the quadratic formula calculation. Let's summarize what we've learned. We solved a cubic equation using a special factorization technique that works when the condition of plus c equals b plus d is satisfied. This technique allowed us to factor the cubic as x plus 1 times a quadratic expression. We found one real root, x equals negative 1, and determined that the other two roots are complex numbers. This method is particularly useful for certain types of cubic equations and provides an elegant alternative to polynomial division or other solving techniques. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.